about it. Yeah. Probably.
Just minimize it, right?
Exactly, and put it. Yeah. This is
the minimum I can do, I guess. Yeah.
This is just use this one.
Okay, but they won't see it, right? Okay, but yeah. Okay.
We've already had some introductions, so we'll keep it short. So it's a pleasure to welcome Cornelius Rampf, who I think many of you know from various activities. And this is his first time in the festival, and we're glad to have him. So Cornelius, as you can figure out, is a very active and authoritative researcher in the Vlassov-Poisson system as applied to cosmology. So he spans some of the areas that we all know and love with some different areas. He did his PhD at University of Aachen. He was a fellow at Nice working with Uriel Frisch and friends, and now is at University of Vienna. So
many thanks, Pat, for the introduction. And also thanks for the organizers for inviting me. So yeah, it's the first time I'm at this festival, and in fact, it's also the first time I'm in an in-person meeting since the pandemic. Yeah, so I had other meetings, but this is the first in-person one. Yeah, so see if I'm not too rusty. Okay, so my overall topic will be based in cosmology, astrophysics. But I will try to introduce everything thoroughly because I was aware that this is a very mixed audience. So, but in any case, if there's questions, please don't hesitate to ask anything straight away. And so I will start with an introduction into the general topic. And basically what we are dealt with in cosmology is on the larger scales is understanding the evolution of dark matter. And that is presumably described by a Vlassov-Poisson description. And this comes also with some kind of challenging to the modeling, especially since dark matter has some peculiar features that are collisionless nature and also initially cold. And because of that, essentially, we have to deal with extreme densities. And this comes with challenging from the theoretical side, but also from the numerical point of view. And lastly, I will also point out some related problems in plasma physics. So I won't talk too much today about the very big picture of cosmology, but I just want to give you like the main sequence of what happens before I can even start talking about my topic. And that is probably you also heard of inflation before. But just as a quick sketch, what's happening is that this is our current understanding is that the universe started with a Big Bang, and the initial conditions was essentially just some vacuum state, quantum vacuum state with some quantum fluctuations, essentially just a Gaussian spectrum, and then suddenly a stage of accelerated expansion kicked in that was driven essentially by a Klein-Gordon equation. And this process had a nice feature or interesting feature that these quantum fluctuations get stretched to super large scales. And essentially by maintaining their amplitude, but the wavelength gets stretched enormously up to galactic scales. And by stretching them to these very large scales, they also classicalize. And that basically provides us the seeds of what we're dealing with later on in the universe. Then comes the plasma phase. I will talk a bit more about this in a few slides, but just like the picture of it is that we have to deal with like a warm plasma. At the very end stages, final stages of the plasma, it's about 6,000 Kelvin hot. So it's not very hot, but still warm enough. And it's actually comprised of classical particles, and they are exposed to essentially self interactions. Okay.
You have an echo just for you, for your. Maybe I can try to.
Or I switch off my audio, maybe.
Yeah, please.
Is it now without echo? No, still.
No, still echo.
I could make it quiet.
Just mute it, possibly. Yeah.
Hello? No, there's still an echo. I can do the following. Now it should work, right? Hello? It's quite stubborn. I put it on completely silent, but it's still talking. Is this annoying for the audience in the Zoom? Yeah, I can blend it out. Yeah. I'm still not fully awake. Yeah, so the plasma is essentially exposed to gravitational electroweak interactions, or self-interactions, so to say. And while the initial expansion of the universe is still continuing, not as fast as in the very initial phase at inflation, but it's still quite significant. And it has the consequence that the whole volume of the universe is expanding too. And when the volume expands, essentially the mean temperature has to decay as well. So it drops essentially because mass is conserved, but the volume changes, so the density changes, and as well also the temperature. And because the plasma cools down, some interactions will eventually freeze out, and that will then be essentially the starting point of structural formation. And in this phase, the electroweak interactions are essentially frozen out, as I said. And because of this freeze out of interactions, the matter, especially dark matter, can cluster non-linearly very efficiently, leading to this highly filamentary structure on very large scales. So I will comment on this, of course, much more in detail. So the main constituents of the universe are, at least according to the energy budget, nowadays we supposedly have about 70% of our energy is comprised of dark energy. Dark means that we don't really understand what it is. We have not much understanding what it, we have some ideas, but not more than that, I guess, yeah. And essentially, it's a uniform distribution of something that is repulsive. So Einstein at the time said it's something like negative mass of empty space. I think it at least captures the idea of it, that it's something repulsing. So it's like something gravity acts in a repulsing way, which is odd, of course, yeah. And the main effect is also that it drives the accelerated expansion of the universe. And this is like shown here in this kind of sketch on the right-hand side. So the main effect essentially is really just that the whole volume of the space is expanding, and because of that, it is very easy actually to take care for theory and numerics to model a dark energy. So this is quite easy. So essentially, you just need to reintroduce some suitable coordinates. Called is usually co-moving coordinates. Co-moving then means basically that you have the observers fixed on these kind of grid points here and here, and once you have chosen these coordinates, you essentially have taken care of dark energy. Of course, a little something comes as well. Dark energy has also a little effect on clustering, but it is at least the main effect of dark energy is taken care of already. Yeah? So it's the tough part, I would say. So, but now comes the more serious problem: is that is dark matter, which is it's 25% of today's energy budget. It's about 6 times more than the visible matter. And it appears to be extremely weakly self-interacting. So except, of course, through gravitational interactions. And also we have good evidence that it appears to be completely collisionless and at least initially cold. So I will come to this coldness, of course, in more detail later on. And so just like an idea why we think that there is something like dark matter, there are lots of probes that on a range of scales, like on galactic scales, like for example the rotation of the galaxy, of the Milky Way, for example, that did not match up our expectations. But on essentially all other scales as well, if you go to like super large scales, on the cosmic scales that we are dealing with here in cosmology, we essentially saw something that the gravitational potential is like something like this orange line here. But what we actually can detect from measurements, for example, through gravitational lensing, was like a big part bigger than what we expected. Yeah. So the main cosmological model is really built up on this hypothesis. But also, as the name suggests, again, dark matter, we don't really know what it is. There are a couple of candidates nowadays that are floating around, but right now dark matter as a particle is really just a very convenient framework to include all these kind of properties that we know from observations. but we don't otherwise know exactly what it is. It could be some kind of supersymmetric particle, although this is rather ruled out these days already, or some kind of axion particle. Who knows? Yeah, we don't know. But the good thing is we just know the properties of it and we can work with it. This is the positive part of the story. But still, since we know some properties, we want to test them, of course, to make really sure that they are valid on a range of scales, or possibly when are they breaking down. And so one side of cosmology is exactly to address these kind of open questions. I mean, what are the properties of dark matter? Of course, also of dark energy. What is the origin of it? So what is the process, the mechanism that generated it? Was it just spit out at the end of inflation as many other particles? We don't know exactly. So after inflation, which only lasted for a fraction of a second, we are essentially left with this plasma, what I mentioned before. And the mean temperature is dropping quite a lot within the first 400,000 years. But within these 400,000 years, we have essentially a plasma that is self-exposed to like a couple of interaction chains. So the main chains are just depicted in this kind of sketch here. So we have photons that are coupled to electrons, and electrons are coupled to baryons, and baryons are coupled to dark matter. So it's a whole system with several interactions that are in principle governed by a fairly complicated system of equations, the Einstein-Boltzmann equations. But there's a very nice feature at these early times, is that since the photons couple essentially to dark matter or to matter particles through several interactions, we have that dark matter essentially, when they come close to each other, they will feel the pressure exposed from the radiation. So basically, as soon as matter always wants to cluster, it's like an interacting force that you just want to accumulate. But as soon as you accumulate, what happens is that the radiation will try to push it out. So what happens essentially is something quite similar like a harmonic oscillator. And we have this kind of picture here that summarizes it quite well. So it's really performing oscillations. And the good thing is that an oscillator is a phenomenon that is fairly linear. Okay, so which means the very complicated equations, the fully nonlinear equations of Einstein-Boltzmann, they are essentially reduced to a linear set of equations. And these one can easily actually calculate by using certain numerical methods. And of course, verify if this is a valid assumption, but I've seen actually some of my colleagues worked on kind of nonlinear effects on these early times, but they are minuscule. You can basically ignore them. They are not really relevant. So it's good for us because we have a quite solid starting point of our calculations, I would say. And the later evolution of the universe, there's a phase transition happening essentially, because the mean temperature is dropping. At some point, the interactions, well, some of them will start freezing out. So in particularly electroweak. So I mean, first the neutrinos, for example, decouple, and then there will be photons that decouple, essentially because the interactions that coupled these radiative particles to the matter, they just become ineffective. And what happens is that suddenly matter is allowed to cluster nonlinearly. And this is exactly what happens on a range of scales, especially also on these very large scales that I'm mostly focused on today. And on these large scales, we can actually work on this gravitational Vlassov-Poisson description that is very accurate. I should also note, I just made really like one line of comment, but I could probably talk about this for a couple of hours because I've worked on this for many years with my colleagues. It's a quite subtle topic, how you can change from like a relativistic description to something that is Newtonian. And I mean, anybody who is interested, I can talk on this also later on or any other time. Yeah? In a sense, one can swap between these different physical descriptions in multiple ways, depending on what you want to do. So I will not talk about this today, unless somebody has interest. So I want to focus first on the pure Vlassov-Poisson equations. I assume that you have seen like a phase-based distribution function before. So essentially, in our case, in the gravitational case, we are dealing with a dark matter distribution function that essentially is just tracking how the distribution of dark matter changes in the six-dimensional phase space. That is the essence, and that is essentially described by a collisionless Vlassov equation, a collisionless Boltzmann equation, also called Vlassov equation. And it is not the most elegant way, and also not really recommended to exactly work with these equations. I will come to this in a second, because they are actually quite full on. It's a six-dimensional or seven-dimensional description if you include the time. So it's not a very elegant way. But in a sense, you have essentially a distribution function that couples through gravity through a Poisson equation to itself. So the matter is here just, again, the dark matter density. And so in principle, one could start solving this equation by suitable technique. But one should do something else before that, I think. And the other thing what one has to do is make the properties, exploit the properties that we know of dark matter. And since we know from various experiments, mostly these are like CMB, so it's kind of decoupling experiments where the plasma is decoupling, the radiation is decoupling from the plasma. And from these experiments, we know that dark matter is cold initially. And that means that if you look on the phase space, this is again just a sketch in kind of 1D gravity, you see that the width in the direction of the velocity is infinitesimal at all times, since you essentially don't have any thermal properties imprinted in your dark matter. So there will of course be much more complicated things happening later on than what I'm showing here, but this kind of property that it's always confined to this infinitesimal sheet that will persist at all times. At all times, the particles, dark matter, will always be confined on this kind of hypersurface. This is a very important property that we can exploit.
So, you don't, especially cold like that, and especially in the early phase, you don't seem to consider collisions whatsoever. So, interactions, collisional processes, or all those early clusters, you never consider.
Between dark matter and
I don't know, your right-hand side here is equal 0, not a collision operator. Or...
Yeah, because this equation is only valid after decoupling. It's very important, because before you would have to deal with a Boltzmann equation for dark matter, and then you would have here, of course, also a collision term that comes from various interactions. But since we are now already in this progress phase, where all these interactions essentially flows out, there are still some residual interactions. This is true. But we can actually include them in a very efficient way. We could, for example, continue using a full relativistic description, also including a Boltzmann term here. But this is a complete overkill, because these interactions between radiation and matter, or also baryons, are very small. So I don't know if it's basically you can deal with that with some kind of rescaling, essentially, an argument based on perturbation theory. Yeah. So because they are very small, these kind of couplings, you can deal with very efficiently with perturbation theory. So this is usually the recommended way how to deal with these kind of residual interactions. And if you want to, but again, this is like a topic that touches like how you actually swap between the relativistic description and the kind of Vlassov-Poisson description. So this is it's a valid point, and I can give you many more details on this. Yeah, but it will completely burst this discussion, I think. Yeah. Another question?
Yes, well, describing the dark matter distribution function here, we don't bother about the matter panel, and at later time, maybe you will be interested in the distribution. So how do you fit that? Is it something like a passive scalar or something like that?
It's also a very good question. So we, of course, we're not ignorant to the visible matters. I mean, at the end, it's us, yeah. So we should not ignore us, yeah. At the end, I guess. So when I say here matter density, what I mean essentially is the total matter density. So in some sense, you're perfectly right. We essentially ignore in this instance here, for example, the interactions that are still residual between the baryons, the visible matter, and radiation. But these are very small. So it actually touches a very similar point as GM right now. So we can include them with various methods, But the simplest way to deal with these interactions is essentially by moving it to an infinitesimal boundary layer. So where you basically swap between different physical descriptions, and then you can incorporate this very efficiently, essentially through a boundary condition. So this works quite well, as long as you are only interested on results on one instance in time. So if you just want to know the distribution of all matter in our universe at one instance in time, this kind of boundary analysis is very accurate and works very nice. But if you're, for example, interested in what we call light cones, so you basically want to see like an evolution of things happening along what you can see in the past, then one has to do something a bit more sophisticated. But it works in either way. Is this my phone? No. Okay. So I will later on also discuss like warm features. But for the next few slides, I will focus on really these kind of dark features where we can essentially confine the dark matter on these hypersurface. So one, or basically there's other ways of course as well, but the way to deal with the evolution of the dark matter distribution in phase space is using a clever parameterization. And that is essentially employed by using Lagrangian coordinates. So probably some of you have made contact with that, but just in case, if not, when there are like essentially two frame of reference that you can deal with if you deal with a fluid, and in a much sense, a Vlassov-Poisson description is also a fluid. It's just that it has a bit more complicated features in late times, but in a sense, it's also just a fluid where we can use like these kind of perspectives. So Eulerian perspective essentially means that you're sitting here, for example, here on this bridge and observing how the river here is floating around. And you see, for example, this like a tracer particle is this boat here. Essentially, it's just following the flow of the river. Likewise, if you employ Lagrangian coordinates, you essentially have an observer. Well, not just one, but many, of course, yeah, sitting on these kind of fluid parcels that follow the stream. And a bit more sophisticated way to describe the same thing is essentially introducing the Lagrangian map. That essentially is, again, it's just a parameterization of the whole phase space sheet. And what it does is essentially it tracks all initial positions of your dark matter particles to its current positions. And I've shown this here on two examples here. We have like two particles that are sitting here on this kind of manifold. And these white arrows are essentially just the trajectories of your fluid particles. So the interesting thing, or from a theory point of view, is that you can simplify the Vlassov-Poisson description greatly with this kind of old trick, I would say. Basically, because you can define the Lagrangian coordinates in a way with this characteristic equation that the velocity is really just obtained by a total time derivative of your current position. It's like a definition, so to say. But with this definition, you can essentially reduce the very complicated phase space dynamics to this simple, basically a Newtonian type of equation of motion that has essentially just a Poisson, like a gravitational force, essentially through self-gravity. And the only non-trivial thing that I'm essentially skipping a bit of details is this kind of subtraction of this last term here. But it's essentially just because we're using these kind of co-moving coordinates, we have to subtract out like something that essentially is following this co-moving expansion. This is exactly what this term is. So it's really just a completely time-dependent term that essentially just describes that the universe is expanding and on average. So the average mean density is just subtracted out here. And this is, so to say, the physical potential, because that drives actually the how particles in this kind of co-moving system are going in various ways. So this is like the physical system. Okay, now I want to quickly also highlight how this relates to like a plasma problem. It's actually quite an old plasma problem, and maybe you can still see it in textbooks. So basically, just compare these kind of equations to each other. You will see that they have very close similarities. Essentially, what happens is that you swap the sign of the interaction, because now in the one component plasma case, you have essentially repulsive interactions, and yeah, but otherwise the modeling at least the equations look very similar. That's what always intrigued me, because when I see equations that I can recognize the pattern, I also know, okay, it's quite sure that many techniques you can basically borrow from one field to another, and that of course is the long-term hope. Also, that some of the techniques that go from cosmology to plasma go vice versa, or plasma to cosmology, as it happened also in the past. So there's one essence of also one idea of why I'm speaking here, so that we have kind of interdisciplinary exchange between ideas. I will later also highlight a bit more in detail some plasma problems that are relevant. But right now, let's go back to the Cosmo case again. So you have basically achieved already the main step, that simplifying the system of equations. This is a bulk part already, but it's still complicated because of this feature that that matter doesn't feel any pressure support. So it means that matter can accumulate very efficiently, and that leads again to extreme densities. And to deal with these extreme densities, one has to make sure that the techniques you seek to solve these equations are accurate enough. And it's just quickly another slide I want to show you. I mean, in principle, you could also work in an Eulerian description and retrieve from the Eulerian description your whole information of the system. But you can track basically either of them, and you would get the full solution from it. Okay, so I want to quickly also say something about simulation techniques. I mean, this is actually one aspect that I think cosmologists, at least in initial phase, have largely borrowed from plasma physics, I would say. So embodied simulation techniques, for example, is one of the most common used even nowadays in cosmology. Well, because we have to deal mostly with very cold distributions, so it's actually a good way to deal with it, I would say. And what it does is kind of depicted here. So you see, it's essentially, I mean, in principle, you work on a continuum description if you work with Vlassov-Poisson. So what you have essentially is you are using tracer particles, and you just hope that you have enough tracer particles to recover most of the features of the distribution. And then, of course, there are more sophisticated ways that essentially is exploiting more like the manifold structure of this dark matter sheet. So what I mean with that is essentially you can, for example, still use dark matter as tracer particles, but then before you, for example, calculate the next time step in the simulation, you need to calculate the density. And the density you basically need to somehow retrieve from this phase space sheet. And you have the choice: you use particles and you use some kind of approximation of this of the particle distribution that gives you a density, or you can also just try to use a tessellation method and try to get a better approximation of your density in this kind of intermediate time steps. And these kind of techniques, or very similar techniques, have been developed since the last 10 years, and they work quite well. This kind of picture here on the right-hand side is a very naive way how it works. When here is really just like a linear interpolation, you would just connect the particles. This is of course not what we do. So we do something a bit more than that. So you basically can imagine of like higher interpolation schemes, and there are also approaches that essentially are trying to track not just like this kind of sheet in the phase space, but also the tangent space of it. Tangent space means that you essentially try to calculate really at each time when the sheet makes a curve in the phase space, you look at the tangents in the space direction and in the momentum direction, and if you have a way to deal with this kind of tangents flow in all directions, you can maintain more of the structures, the properties of your sheet. So these kind of state-of-the-art techniques basically are usually based on this approach from Jens Stücker, and they work extremely well. So the figure I showed you, one of the first slides, essentially is obtained from this simulation technique. And lastly, there are of course also full Vlassov-Poisson simulations, and where you don't force the dark matter to be confined on this hypersurface, but you let it allow to have some kind of thermal distribution. These kind of investigations are particularly relevant if you deal with like residual warm features, especially if you consider the couplings with massive neutrinos. So we know that there are neutrinos in the universe, and we also know that they have a mass. So dealing with massive neutrinos is quite a subtle, delicate point. There are various ways how to deal with it, and one approach would be by direct simulation of this full Vlassov-Poisson system. And it's mostly based on papers of Tanaka and Yoshikawa from a few years back. Okay, so this slide is a bit heavy, but let me just walk you through it. I want to try to explain what the difficulty is in what we're dealing with. And for this, I need to switch on a bit of details. Otherwise, I'm not sure if I could keep you on what's happening. So first of all, what I want to show you is if you start with like a distribution of dark matter that is initially just we call it monokinetic, which means you just have initially like a velocity field, but no velocity dispersion. At some point, because of the interactions of dark matter with itself, the streams will essentially start to build up. When bump up, or whatever you can call it, you can see it here in its phase space. You see here the velocity in this direction here, for example, and here the current position. So initial time would be something like the green line here. And because of the gravitational interactions, what happens is that you have kind of an upturning point. And this point, when the tangent here is exactly vertical, we have an instance that is called shell crossing. And this is a crucial moment in the phase space history. That happens not just once, but it happens also at many other times later. But whenever you have these kind of tangents that are completely vertical, this is an extreme scenario where you have essentially infinite densities in the phase space. So this is also shown here. So if you have, for example, look here on the time after shell crossing, which essentially is this blue line here, you see that you have these kind of densities here. Essentially, when the phase space behavior changes drastically, because in the exterior region you have a single stream. So we only have like at each particle location we have one particle, but at these later times we have actually many more particles here, for example 3 particles and so on. And exactly at this boundary where you have in the present case a single stream regime, the exterior regime, the white regime here on this side, and this kind of multi-stream regime where you have like in the present case 3 streams. These regimes are accompanied by essentially a phase transition and with infinite densities, even at later times. And to explain what happened there, one can also look this up in Lagrangian coordinates. So essentially, if you have a fluid description, like a fluid that is compressible means that it can really like collide and density can change drastically. Then you can essentially link the mass conservation law to the Jacobian determinant of your particle trajectories. Okay, so this is at earlier times just this expression here. And essentially what I've just tried to explain is this is essentially the statement of mass conservation. You see here essentially on the right-hand side of this equation, just the density at uniform density at some initial time. So really early times where the density is efficiently just uniform in Lagrangian coordinates. And at later times, mass should be conserved too, right? Because we don't have any collisional interactions, at least in this model. So what you do is essentially you can link these kind of laws of mass conservation to the Jacobian, as I said. And essentially, when if you work in one space dimensions, the determinant would be really just the space derivative in the Lagrangian direction. So in this lower left figure, when the derivative here essentially is 0, you would have essentially a vanishing Jacobian in the 1D case at least. And something very similar happens also in multi dimensions in 3D and so on. But crucial is whenever you have these kind of tangents that are completely horizontal in this figure here, it's essentially the same problem that I explained here on the first figure on the right, top right, that the density goes to infinite. So these kind of blue shaded regions, they resemble exactly the same time in the phase space, essentially. Okay, so there's been a lot of progress by investigating the Vlassov-Poisson equation in cosmology, and one of the, well, maybe two pioneering works, I would say. Well, not just, I mean, Peebles, he got a Nobel Prize just recently, so he did not just like this, what I'm pointing out here, but he did many other things, of course. But perhaps even more crucial for Vlassov-Poisson was the work of Sedovich and also Novikov. That is a quite interesting description because it's so simple that I think one understands the idea of it very quickly. So essentially, if you think that the universe has only one space dimension, it's of course a radical simplification, then you can solve, at least in Lagrangian coordinates, the Vlassov-Poisson equation exactly until shell crossing by essentially this kind of ballistic recipe here. Yeah? So what it tells you is here essentially that the current position of your particles is essentially just their initial position plus a velocity and weighted by a time. So it's really a super simple shooting particles in various directions, and you know exactly where they are. So of course this is a very nice physical description of I would say a quite complicated problem, because if you want to deal with the same problem in Eulerian coordinates, the solution would look completely different, much more complicated. I will come to this also in the next slide, just quickly here. So Zelovich was one of the pioneering works, I would say, and there have been also other works that tried to circumvent the kind of drawbacks of working in this kind of simplified model of a one spatial 1D universe, so to say. And that was not so easy. It took a long time. I mean, basically based with a work with Will Fish I did a few years ago, where we basically were doing some kind of deviation from this one-dimensional setup, and this was the first time where we actually were able to get analytical shell crossing solutions in a 3D setup, but of course still with a simplification in mind. And just very recently with Oliver Hahn, who is based also in Vienna with me, we worked on essentially on the completely 3D case, which requires also some kind of numerical methods. I will come to this later. So all these shell crossing solutions here have at least one thing in common, and that is they all exploit Lagrangian coordinates. I will also show you again on the next slide why, again, not Eulerian, but for the moment, whenever you have a problem that essentially comes with singularities in mathematical physics, you would like to know the transformation that essentially is removing the singularity. I mean, you can't remove that singularity because it actually is in your system, but at least you can move into a coordinate system where its effect is as weak as possible, that you can still deal with it by, you can grab it still by hands without it running it through your hands, basically. Yeah. So, and one way to do this, solve the Vlassov-Poisson equations, is exactly using Lagrangian coordinates, because they are essentially what we call a desingularization transformation. So it allows you to work with singular problems in a tractable manner, so to say. And one easy way to understand this is very simple. So at the shell crossing locations, I mentioned it before, the density goes to infinity. So this statement that the density goes to infinity is equivalent in Lagrangian coordinates to the Jacobi determinant to go to 0. So you turn infinity into a 0. It's quite a nice trick, I would say. So based on this kind of Lagrangian setup, there have been a couple of important works, especially the work of Sedovich and Fish, 2013. That essentially was the first paper that tried to solve the Vlassov-Poisson equations essentially by means of a Taylor series. Yeah. So, yeah.
So you're treating the shell crossing as something physical, but don't you expect collisions, participation, that regular?
Also, good point. So you could argue, okay, this is just like a reduction of a problem. So why are we dealing with these singularities? The problem is, first, there are many answers to this question, so I don't know how even to start. Yeah. So the first thing essentially is that if you work on large scales, and you can always say, okay, there should be some kind of thermal spectrum in your dark matter distribution, and that might regularize things. This might be true. But the truth is that many of our techniques that we use actually exploit exactly these kind of dark matter features that I explained before. So we use actually exactly these properties in a host of simulation techniques and also in theory. So, so in some sense, we need to understand if this kind of effective description that we're dealing here is meaningful, and for this we need to take everything into account, because if the density would blow in your face essentially and would lead to some things that you can't handle by any techniques, then we could not even work with these kind of techniques anymore, right? So then, I mean, the conclusion would be we have infinite densities, our simulation techniques don't work. We need to now introduce some thermal features. Okay, this would be one way. This is kind of a pragmatic way to see. I prefer to actually look at it from the other perspective. The other perspective is that all over in physics, we're not really dealing with a lot of approximations, but we are actually considering limiting behavior. So, for example, if you have a pot with water and you want to heat it up, and you want to basically measure the temperature, you don't measure the macroscopic motion of your particles, but what you do is you perform a thermodynamic limit, and then you can define the temperature and stuff like that. This is meaningful. So one has to distinguish, and I think it's very crucial, between an approximation and a limiting behavior. So this is why we take these singularities very seriously, yeah? Because they appear in anywhere in physics, not just in the universe here at the shell crossings, anywhere where you have essentially a phase transition. Anywhere when you have a change of phase, something happens quite radically in the phase space. As I showed here in this other slide here, this is also sort of a change in phase space, right? Because you change here from a single stream behavior to a multi-stream behavior. This is a radical change in phase space. And yeah.
I guess I'm asking if you are treating what happens inside the region as physical, the multi-value thing, or like the thing I'm familiar with are shops like inverters, where you just like there's a viscosity that regularizes and happens.
Yes.
So I'm not sure if I understood if there is something like a dissipation that actually regularizes this, or you want to track the multi-value.
Okay, we need to track the multi-valued regime, because I'm also familiar with Burger's equation. It is also used in cosmology but it's a simplified setup. Basically, in cosmology, it was used to essentially ignore all these kind of regions where you would have like several streams overlapping. Because it's based on a very elegant trick on Burger's equation. If you add essentially a viscosity term, then you have energy dissipation, and that basically prevents this kind of odd features in phase space. But unfortunately, these odd features, they are highly relevant in cosmology. So what you see here is a three-stream regime here. It will continue curling up in phase space. At later times, this is just the initial phase, what I'm showing here. At later times, it will essentially give you hundreds of streams at one location. What does it mean? It's essentially a halo, a dark matter halo. Okay, so whenever you have like formed regions where you have compound structures in the universe, you have multi-streaming. So these things are essential to actually understand the large-scale behavior of dark matter. It's essential. But I mean, I love Burger's equation with this trick. It's great, based on Hopf-Kohl, basically. It's a great model, and it has a lot of applications, I would say. But it's unfortunately one of the drawbacks, I would say, that you actually kill all the multi-streaming, because this is what we observe here.
Sorry.
Yeah.
Following up on that, where you have those multi-value solutions, you have those thin sheets developing. You know that this is probably where you would have all of your structures, and you will have all of the distribution of galaxies later, and etc.
Yeah.
And there you know that you have other source terms which are clearly not taken into account in your equations.
Yeah.
So I'm just, I think, since you're looking at very, very long cumulative times,
Yes. Yeah.
and you're not taking production terms, which will exactly happen there, why do you need that degree of sophistication without taking your source terms?
Okay, very good question. Yeah. It relates also again a bit to this problem of why we use with the simplified description and then take these problems very serious. Yeah. So basically, these kind of multi-streaming regions, they are not just relevant for very small scales. For me personally, small scales is galactic scales. You know? So you need to look a bit bigger to see my small scale, large scales. Yeah. And on large scales, you need to take also these properties very seriously. Yeah? So there are simulation techniques or like lots of papers that worked on using like warm features of dark matter, and a host of observations do not match at all. Okay, so it starts already at decoupling time that if you add some temperature to your dark matter, the distribution is completely off. It doesn't match what we can what we see with all these probes like from Planck and WMAP and so on. So there's a lot of problems. So it seems that we are actually forced to deal with these kind of odd features, because if we are try to get rid of them, then it doesn't match with our observations anymore. Yeah, yeah. It's kind of yeah. So this is my what I also tried to answer before. So we have to deal with phase transitions, and they seem to be really physically relevant, irregardless if you believe that they have zero temperature. Yeah. Yeah, there's something radical happening in the distribution of dark matter. This is a fact. We just don't know exactly what happens, but we know that it's very good characterized with this kind of behavior with this simplified model. And of course, then comes I think your second part of the question was how to relate this to like rather small scale problems like galactic problems. This is a completely different story. So it's a very complicated and active part of research, how to actually relate this kind of evolution of dark matter and include also interactions again, like on very small scales. So because on small scales, we know on galaxies, we have a vast range of interactions between like dust and radiation again. We have a lot of baryonic effects there. So these things, for this one, that has to swap the description again. And one is usually right now using essentially full-fledged numerical simulations, hydro simulations. And one way to kind of connect what we're doing here with these hydro simulations is that they all, in a sense, have to deal with the same problem, at least for dark matter. But on top of that, they have even more problems to deal with. Yeah? So I see it from a pragmatic point of view. First, understand like the leading order problem, which is dark matter in phase space. And then comes the small scale stuff that is highly non-trivial as well, of course, but you first should get the dark matter distribution right. I think it's very crucial.
Can I ask something since we're in question mode?
Yes.
So you mentioned the analogy with compressible gas dynamics. So in compressible gas dynamics, you get a shock. Then you would have shock conditions. Follow the shock. You know what should be conserved across the jump and all of these things. But you seem to be going beyond the time of the shock, just carrying on.
Yes. Okay, the shocks you're talking about are more radical, so they are accompanied with more radical behavior in phase space. I mean, I will later on show you what exactly happens, like in detail. At these, this is kind of also a shock what happens here, but they are actually not as bad as the shocks that you see with like dust interactions and so on in AGN feedback. They're weaker. I mean, you can basically characterize the level of seriality of your singularities by just looking locally on a Taylor expansion. And well, here you would normally say, okay, the density goes to infinite at these shocks. This looks like a very bad problem. Okay, But this is not really true because the density is not really a phase space variable. It's not really required in the simulation. What is important is that that the gravitational force remains finite, that it doesn't blow up. And this is actually possible if you do this in Lagrangian coordinates. You can see that you can actually follow these shocks without losing, in principle, accuracy. With some pitfalls, so I agree with you, but you need very high resolution simulations to do that. But we can also do it by theory, actually. So we can actually calculate what exactly happens in the phase space. And I can assure you that the density going to infinite is not the problem. It's more about other changes in phase space.
So continuing in this vein of discussion begs the issue of stability. You know, in Vlassov systems, of course, you have many possibilities, particularly what comes to mind are two-stream stability. So, I mean, how do you assure the stability of these structures, or do you?
We do, yeah. We know that they preserve the theorem, for example. So, I mean, the most important theorems that are basically tied to this description are based on Hamiltonian principles. And because of that, they are tied to Newell's statement of incompressibility in the phase space. And these things are preserved very well. We can calculate this in simulations. And so the code is the codes that solve that are usually based on symplectic integrators, and they are preserving these stability criteria quite well. Yeah. So, but I will come back to this. Yeah. Actually, with time, is it okay? Okay, you're fine. Okay. There are lots of questions, so I'm completely lost of time now.
You can go sailing on almost another hour.
Okay.
At some point, people will want coffee.
Yeah. Me too, actually. Yeah. Okay. So I was on that slide, but only halfway. Okay. So essentially, let's go back to the fundamental problem again, and let's switch on the details later on again. So one way to deal with these similarities is, or you can also see it back to the question of the gentleman, what we should do with these kind of shocks or similarities. One way to actually investigate how similar they are, one of the most powerful tools that I'm aware of are actually Taylor series. Because once you have a Taylor series, you can start calculating things like radius of convergence and so on, and then you know exactly what happens, in the phase space and how bad it is. Yeah. And this is essentially what has been happening the last few years too. So once this pioneering work of Seligovsky and Fish occurred, couple of groups started to take this serious, this kind of looking for like a convergent description, and or more important, when exactly or under what circumstances the convergence of this Taylor representation will be lost and why, and how radical these kind of loss of convergence is. This is very crucial, also especially for stability questions for simulations, of course. So there are a couple of ways how to do that. In a few cases, especially in these cases from here, we are actually able to do this by analytical means, essentially because the setup is so kind of simplified that we can actually calculate the convergence, disk of convergence exactly by elementary means. But in general, if you are, of course, we're interested in a universe that begins with random initial conditions. I mean, I told you in the initial phase of the talk that we have like a Gaussian spectrum, essentially, of density fluctuations. So this is something, of course, that doesn't apply to this kind of simplified setups. So doing this big step from simplified toy models, so to say, to the full Gaussian case is not easy, and this is also why it took quite some time. But once you do that, you can also, of course, calculate all these kind of properties of your diameter trajectories by means of investigating essentially the asymptotic behavior of your Taylor series. So just one slide, because I'm really writing on this why Lagrangian coordinates and why not Eulerian coordinates. And I think this also has a lot of, it touches a lot of fields beyond cosmology because the problems are kind of universal. So if you are in a Eulerian setup and before shell crossing, you have essentially an fluid description that is exactly the same description as a Vlassov-Poisson description, but now in Eulerian coordinates. So I'm working with fluids for quite some time. So I kind of like these equations. They're still nonlinear. There are a lot of nonlinearities in here that are kind of difficult. But for example, by using these kind of representations by a Taylor series, you can actually quite efficiently calculate solutions of these equations. These are fully nonlinear equations, and you try to solve them basically with Taylor series. And it works actually to some extent quite well. So there exist like very simple order recursion relations. So essentially, you just need to choose appropriate boundary conditions, and then you can start calculating all these Taylor coefficients. These are the unknowns here, and you can calculate it to any desired order essentially. And you might be very happy about that, but it's unfortunately not as straightforward in Eulerian coordinates. So it's just again like a simplistic setup here, one-dimensional gravity. And I'm just showing here actually a quite early time. If I would show you later times, this would be another talk, I guess, because something very radical happens that I'm just working on right now. But even for these times, half the time of the first shell crossing, you see that the convergence rate is very slow. Yeah, I mean, you see the exact solution is the dashed line, and you see like the first two solutions, the first and the second solution, are very far off from the exact solution, even at these very early times of the gravitational evolution. Yeah, I mean the density is just it's still quite small. It's not even close to infinity. Yeah? This is where the target would be to detect a shell crossing, right? So this is very far off. So second order is very far off. Second 10th order works quite well at these intermediate times. But as I said, I mean we can also talk about this in more detail. What happens in Eulerian solutions later? This is it's not at all doing well in Eulerian coordinates, believe me. And one reason for that is essentially we can explain this by various arguments. The first one is that the convergence rate is very slow. And why? Essentially, the problem of solving Vlassov-Poisson for dark matter is essentially a problem of convected motion of your particles. This is the essence. And you couple it to a Poisson equation. Of course, this has to be dealt with, how to exactly calculate the gravitational force. But in a sense, the fluid particles, they really just follow convection or advection, yeah, advected. Okay. And these convected terms, they appear here, for example, and also here's another one essentially. And they are the reason why the solutions in Eulerian coordinates, no matter if it's Cosmo case or like incompressible Euler or even Burgers, for example, they are very bad essentially because of that array. Yeah? And one reason is essentially that we are just working on essentially not just like an infinite density edge shell crossing, that of course is a very nearby singularity. And as some of you probably remember, singularities are very decisive for detecting a disk of convergence, because somewhere on the disk convergence of a Taylor series is at least one singularity, and we know for sure that the density goes to infinite at shell crossing. So this is already a bad thing. It means that we cannot go further in our descriptions up to the moment when the density goes to infinite. Yeah? But there are even more singularities, many more that are in a complex time domain, and they are actually even more severe. So loss of convergence happens much earlier. But again, this is I can talk about this, but this takes a lot of time. So let's go back to Lagrangian solutions. I did not even show here the Eulerian solutions because they would be so bad that you would easily see it. Why you should not use it. And so what you can see here is essentially the first numerical verification of analytical shell crossing solutions based on this paper by Sagatoria Colombi a few years back. And what you see here essentially is two slices through the phase space by initial conditions that are kind of simplified, but still physically meaningful, at least. I mean, to at least detect how good the performance is of these Taylor series in Lagrangian coordinates. And what you can see is here, if you are in quasi one-dimensional setup, quasi 1D basically just means you have something that is dominantly in one dimension, has a lot of seeds, but in the transverse directions, essentially it has almost no grains. So it's only weakly some wobbles, but in the main axis you have like a very strong amplitudes. And this setup is very well modeled by low-order solutions of this what we call LPT. These are just essentially solutions based on Taylor series. And in this case, if it's 10th, it means just that we include the first 11 coefficients. So it's a very fast convergence. In this case, when the initial data is close to quasi 1D or close to 1 dimensions. If you go to a bit more realistic setup, you would have like a generic collapse will be something with like if you think about like a triaxial system, you have like some amplitudes this direction, this and this, so all the directions, and they all have more or less roughly the same amplitude. This is a good starting point to investigate like realistic collapse, I would say. And there you see that you still have some convergence. This red dashed line converges still quite nice to the simulation result, but not as good as in the quasi 1D case. So what we learned from this important paper was something that that the conversion speed depends crucially on where exactly you sit in your universe and how strong are the grains in the various directions. It's very crucial for the speed of conversions. That was, at least for us, a very important lesson we need to learn. And just like a year ago, we Oliver and Han and I worked on this paper where we essentially used like a semi-analytical setup where we essentially we are calculating the unknown trajectories on a mesh, and essentially are just calculating all the Taylor coefficients to some sufficient or high order, and investigate like easy properties of what happens essentially with these kind of solutions truncated, because you can't go to infinity, at least not very practical in this setup. So you basically look at truncation errors when you go to a certain order in the Taylor series, and then you see how large are the truncation errors based on that. And this is essentially summarized in this figure here, where you see essentially a truncated Jacobian determinant, and it's really just essentially tracing what is, well, estimating what a truncation error would be roughly. Yeah. And you will see that if you go to higher orders, it essentially turns into a delta peak, I would say. That basically means that the truncation errors are getting very small if you go to sufficiently high orders. This is already some kind of weak confirmation of convergence. Now the question is, can we do this a bit more rigorously? Yes, we can. Basically based on asymptotic extrapolation methods, which is a heavy word, but the idea behind this is actually, I think, quite simple. Basically, you if you have a Taylor series and you want to know its radius of convergence, which is here called R, you can try to get the radius of convergence by taking the ratio test. So essentially, you just take subsequent ratios of Taylor coefficients, and by showing this in a graphical way, you plot this essentially over 1 over n. You can graphically extrapolate to n to infinity, because this convergence radius here is defined by taking the limit n to infinity. And by simply plotting the thing over 1 over n, you just need to go to 0 in this x-axis, and then you get an estimate of your radius of convergence. This is, of course, only valid if the singularity is really has a very simple pole-like structure, so to say. In the more complicated way, you need to do a bit more sophisticated ways to do that. But in the present case, in the cosmological case, we can actually do that, and the conversion is quite nice. And that basically tells us one lesson we learned from this paper was that the convergence radius actually is larger than the first shell crossing time. This is a good thing, because it means in Lagrangian coordinates we can evolve everything at least until shell crossing time, And at some point later, there might be lots of conversions, but this is not relevant for us anymore because then you need to switch your description anyway already. But we can actually exploit this approach now and can really calculate shell crossing solutions in 3D because we know that the convergence radius actually is larger than the physical validity regime of our underlying equations. Okay, so I will now just quickly show you what one can do beyond shell crossing. This is also still quite active research, but the idea of these approaches are summarized. I think they are still kind of intuitive, so I try to explain it here. So let's go quickly back to the Vlassov-Poisson equation that has this structure here. So it is really just telling you that the acceleration is proportional to a gravitational force. And this equation is also valid after shell crossing. It's just after shell crossing, you will have then at some locations in space, multiple fluid streams. And all these fluid streams contribute to the density, of course, right? You just need to sum up essentially the densities at your local value or like current location and sum up all the densities that contribute to the total density. And this is essentially what happens. And one way to calculate this is essentially using the Dirac delta. So one can essentially calculate the density by using this exact description. And this is essentially what's happening is it's really just picking a current location and sums up all the fluid streams and calculates the density from all these fluid streams at this location. That's what's happening. And so the theoretical meaning of this is fairly straightforward, but its consequences can be quite radical. So one thing is that to calculate such things in theory requires some kind of normal form techniques that I will try to summarize in a few slides, in a few moments. But one lesson what we learned is essentially that despite of that the density is going to infinite, we basically hand-wavingly you can see it also here. The Poisson equation has two derivatives on the Poisson potential, but in the equation of motion there's one gradient less. So one lesson very important is when you have something singular, taking derivatives costs a lot. If something is singular, when you take a derivative, it gets even more singular, and so on. So one has to be careful how many derivatives you take on a singular problem. Essentially, this is like the hand-waving way you can see already that the singularity is appears weaker at the level of the equation of motion, just because of this counting of derivatives already here. So the idea is how to progress at times before shell crossing and 2 times after shell crossing is essentially twofold. So it's a kind of a multi-time stepping method, but with if you just want to do like shortly after shell crossing, it's essentially just one intermediate time step. So the first time step is you solve the trajectories up to some point at shell crossing point, and using the Taylor series approach, for example. And then you can actually provide fresh boundary conditions at this shell crossing location. Why? They actually remain finite, the boundary conditions, because in Lagrangian coordinates we don't have to prescribe the density, but more like the features of the trajectories, and they are not infinite at shell crossing time. So at least in Lagrangian coordinates we can prescribe with no harm initial conditions, so to say, at shell crossing for a refined time step. And then you can actually calculate the equation of motion in an approximative way. The approximation here is subtle, so I need to underline it, I think. So just compare it here. Essentially, the gravitational force depends on the true Lagrangian trajectories. Okay, but this is the unknown quantity. This equation here we want to solve for x. And one way to actually go beyond shell crossing is exactly exploiting that. So if we calculate this equation, which is a simplification, okay, because it tells you that the force at shell crossing is exactly given by the solution that we obtained prior shell crossing or until shell crossing. This is essentially an iterative scheme that allows you to do also higher order refinements. Of course, it would be just the first refinement, but this allows you actually to calculate things even after shell crossing. So this equation here is still exactly at shell crossing, And what we found is that this equation is even still meaningful for short times after shell crossing by using this kind of approximation here. To do this, one has to use some kind of normal form techniques. This is, I will not go into details right now, but open for discussions, of course. Just show you the performance, basically, what happens. So this is essentially the phase space on the top panel here, zooming in into the first multi-streaming regions. The dots are the simulation result. This is actually a very high resolution simulation. This is like, it's just a one-dimensional problem here for simplicity. But the number of particles is, I think, here more than 10,000. This is quite high, I would say. Huh? And so I'm also not showing all the particles. I only show a few of the particles. Otherwise, you will not see much. But you see that the solid line is essentially exactly overlapping with the simulation results. So you see essentially things are agreeing between completely independent measures. One is theory, and the other one is like a numerical simulation. And both can, in principle, calculate the density that goes to infinite at these values here. But again, this is not the crucial aspect. The more crucial aspect in phase space actually happens to the phase space variables. Phase space variable is essentially in Lagrangian coordinates the momentum and the current position. Or if you want to see it this way, if you take a time derivative of your current position, you get the velocity in Lagrangian coordinates. If you take another time derivative, you get the acceleration of your particles, and so on and so on. So essentially, by taking time derivatives on your particle trajectories, you can actually see at what level of derivatives you get things that blow up in your face. And what I'm showing here is the acceleration here on this bottom plot. And you see that there's nothing blowing up, but what you see is that there are non-differential features here, 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 and here. And if I would show you now the next time derivative, you would see things being either discontinuous or even worse. Some of them are actually infinite. So you have a blow up, essentially, on the level of Vlassov-Poisson, but it is a fairly weak blow up. So it just tells you that at the third level of derivatives, we have things that are singular. So this might now sound for you like, okay, this is hidden in the details, so to say, of your result. But these are the crucial limitations of at the end of your simulation you're dealing with. Yeah? Because when you take derivatives, you do this, of course, also in simulations. They can make a problem for you. Okay, this is another singularity. It's a bit non-trivial, so just quickly sketch the idea. So I'm showing here the phase space again for at times earlier and at shell crossing and after. What I'm showing here, in contrast to the other figures before, I added some asymmetry so that you can see that here it's a bit higher than here, lower, so it's slightly asymmetric. And the boundary conditions is still fully periodic, so there's no cheating. So it's all like the mean density is still uniform as it should be with our initial conditions. And we can also easily use these kind of squeezed or asymmetric initial conditions to calculate shell crossing solutions. That's quite straightforward. But now, at the time of shell crossing, I think one can also guess what happens in an intuitive way, because this kind of motion is kind of asymmetric. At some point, you get this configuration here, and now you can think about that this part of the particles are pulling essentially this one particle here in the center to another location, just because the gravitational pull is a bit stronger on this one side than the other. And that actually is another singular behavior, because that particle was initially at rest. It was really just like a spectator particle at the origin in space and time, essentially. And then suddenly at shell crossing, it starts moving. So it switches on and begins to move in a non-trivial way. This is another singularity that we detected in this system. So all these features, we have classified them essentially, and you can basically calculate this also from a high resolution simulation. And we got a very good agreement, at least for this fairly early times. This is a crucial time here, because this tells you what kind of singularity you're dealing with. At later times, we could refine it, but it was not so important for us. It was more important what exactly are the circumstances when the density goes to infinite, which is exactly happening at this time here. So not everything is understood. Definitely not at all, I would say. So I just want to give you like a status report, basically where we are at. So this is again really just again a one-dimensional toy model, but it summarizes quite well our understanding, I would say, on this fairly complicated problem later on. So if you these are just selected trajectories just distributed uniformly, and they start to essentially collide. And we have here at this point here the first shell crossing. So in one space dimension, these solutions up to this point are exact. So in all these three figures, these trajectories are exactly coinciding, at least until this time here. Okay. But then comes after shell crossing. Yeah? So the model of Seldovich is really just shooting particles in a ballistic way with an initially prescribed velocity. So in the specific coordinates we're using, they have zero acceleration. Okay. But after shell crossing, there are accelerations basically that are pulling particles back into the center. You know, you imagine you have particles that are crossing each other, and Seldovich would just say they would just continue their way at all times, which is of course not true, because you would have like a pull that pulls the particles back again into the center of the potential. And that basically this feature we can capture at these early times quite well with this kind of theory that some of my colleagues and I developed in the last few years. And if you compare it with the simulation, we're doing a good step in the right direction, but we're still quite far off, I would say, because what you see here is this is the first shell crossing, and we actually predict the second shell crossing. So second shell crossing would just mean that you have you move from a 3-stream system into a 5-stream system for topological reasons and so on. So this we can predict already, which was not known beforehand. But you can also see that the structure at late times is still deviating quite largely from a high resolution simulation. So there's still a lot of problems we need to figure out. And yeah, and it's important because I mean this is a very ideal setup also even for the simulation. So we're doing the simulation a favor essentially by showing you this here right now. But if I, for example, add some kind of asymmetry, the simulation would also have some troubles. So we really need to understand what's going on there in detail to make sure that the simulations are actually sufficiently accurate.
Is the asymptotic state here going to be a kind of wound up state?
Yes.
Yeah.
So I think I have a video at the end. I can show you this video. So it will really spiral up like a snail house. Maybe you can think about that in phase space. So it's like first a 3-stream regime, and then you would further, like somebody is like just rotating this whole thing, and it will develop more and more streams in the vertical directions.
So with a coarse graining, I mean, you could conceivably prove almost a homogenization kind of result, right? That it would fill some area.
A coarse graining, we apply this tool, and for very similar methods, yeah, it's true. I mean, for example, if you want to work on effective descriptions, that's exactly what you would do. You would try to essentially smooth away these kind of multiple stream regions, and then you can show, okay, you can just use one theoretical model to calculate the effective fluid, but then you need another method that gives you the small scale behavior. And I think this is going in the direction that you asked for.
Yeah, I mean,
and
it
yeah,
becomes like a variation on Prandtl-Bachelor.
okay. Yeah, so there are lots of investigations in that direction too. I mean, especially with effective descriptions in the last few years. But at least I haven't learned more than what I'm showing here, because this is essentially the essence. And the effective description is essentially trying to put a carpet on top, trying to. This is my point of view. I don't want to make any radical political opinions here. Yeah.
The effective description would in principle go further in time.
Yes. Yeah.
At the cost of some assumptions.
Yes. 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 So I know they are very powerful effective descriptions, and they are all overused also in cosmology, of course. Yeah. But here, the level of degree of seriality for this, one has to switch on some details. Later in the applications, I fully agree with Pat. Yeah? So one has to find ways to deal with this in an effective way, really in a literal sense. One has to find ways how to calculate things in a efficient and especially efficient way, because things are very complicated. Also in cosmology, we need to run very large simulations. So we need to find not just accurate methods, but also highly efficient and fast methods. That's one of the crucial things. So one motivation of what we're doing here is basically the same spirit. We're trying essentially to, in the spirit of effective descriptions, we essentially show you what the effective description has to handle with. Yeah. So that gives you some idea of, you think about an effective fluid, then you essentially do some coarse graining, and then you need to introduce some counter terms. And these counter terms, they of course have also some temporal behavior. And we would basically can estimate what the behavior is of this at short times. So we can actually provide information to this effective fluid description in some sense, without being agnostic around it. I mean, this is at least how I looked at it initially. That because in an effective description, I mean, one of the ideas is that you introduce essentially free parameters that are not allowed by symmetry, and then you try to match these theories by experiments, for example. And I think one can even do better than that. I think by using input from theory and to actually give you a knowledge of what happens at these extreme locations in phase space, and that gives you a feeling what the counter terms have to deal with, essentially. Okay, so we're doing time. Okay.
Presumably, several of these structure singularities appear in the space, or it's just one place because it shows
What I showed you here is really, I mean, I tried to do it pedagogically. Of course, what you would see not just like one collapsing structure, but you have Gaussian initial conditions. You would see in one corner directions like multiple like curling up of phase space, essentially at just different values at x. And then of course you need to switch on the other corner directions, so it's a very complicated setup. Yeah? But what we are doing here at this, at least what I wanted to show you today, is essentially really based on a very tailored problem that we understand fairly well. And because I think by doing so, we can exactly see what the problem is. Because if you switch on too many details too fast, then you might lose some of the features. This is at least my worry. So my approach is, or not mine, just of many of my colleagues, to try to focus on the things that we understand, and then try to build up the complications one by one. Even also with GM's question with boundary conditions, there are so many things that I completely ignored today, basically, because the problem gets quite complex. I'm not lying here, yeah? But this is one essence of it, yeah, the problem. Yeah. Yes. Yes, we do. Yeah. This is very generic. So if you, for example, use like a sine wave collapse, or sine wave, I mean, really just you have velocity profile that looks like a sine wave in space. This is, you might think this is a completely unrealistic behavior, but this is not really true. I mean, there have been lots of papers in cosmology, for example, in the 80s by Bardeen, and that basically showed that what is more crucial is the behavior at these kind of critical points in phase space. So that it's a periodic function like a sine wave doesn't matter. You can add like another coefficient or something completely random. What is crucial for these kind of methods to work are precisely the behavior of the normal form. So this kind of behavior that you have this kind of S shape in phase space that happens in a generic way, no matter what your initial conditions are. But by reducing it, at least for this presentation here, to like a sine wave initial data, I'm actually not really cheating, because what I'm doing here actually, this was essentially one of the complications when you introduce if you go beyond a simplistic sine wave model. So you will get another singularity, but this is the one that we detected essentially. So what this means essentially is when you have no asymmetries here, this is something. It's a simplified model. I fully agree, and this is true. Okay, because what you expect is that you have a local Taylor expansions in space that is to some extent asymmetric. So that basically drives you this kind of asymmetric behavior here and here, for example. This is what you generally expect. And then it gives you really another singular behavior, but it's not the worst singular behavior, I would say. This is just one of the three. Yeah. So all the singular features that I showed you today, they're completely, they appear in all generic collapse scenarios. It's just dissected essentially, where they come from. Okay, so last few slides. I think this is one of the last few slides. Yeah? Just quickly highlighting the connections again to some of the plasma problems. So I showed you before kind of one component plasma. That I mean, this is kind of notation that that I've used in this paper recently, but essentially the equation of motions are in principle known. I mean, there's also a very nice review of Escane et al. And but there are also perturbation theory techniques applied to these equations. But at least to my knowledge, usually they are focused on Eulerian solution techniques. And I have not looked into details, so I can only speculate. But I would not be surprised to see similar problems with Eulerian perturbation methods also for these plasma systems. Essentially, also because you're essentially dealing with convective motion here. And so very similar problems should apply here in principle, if one is interested in such expansions. Another interesting correspondence is the beam plasma instability. So where an electron beam moves in a background plasma that is supposedly cold. And what you essentially have is a two-fluid system. What I would explain it. Yeah? So you have like two components. Like one is the electron beam, the other one is the background plasma. And in principle, you could of course just couple it gravitationally with just summing up essentially the two densities from the plasma and from the beam. And in a similar way by using this kind of Dirac delta trick. But this is, I think, not normally what you do. What you normally do is you try to essentially include the plasma response in terms of a dielectric. So basically, you're modifying essentially this kind of Poisson equation in a way by including the effect from the plasma in terms of a modified Poisson equation that then in turn turns into some type of equation of motion. Then, so it's if you. I mean, I'm not sure how many of you are familiar with these works, but I can highly recommend this paper of O'Neill. It's very old, but it's a very classical paper, I find. And what I wanted to point out is that these system of equations are, of course, also known in cosmology, but then, of course, with a different sign, first of all. But this kind of two-fluid systems, they are very common in dealing with more realistic setups of structural formation, because as I don't know who was it, but somebody pointed out that we should not ignore baryons, for example. One way to include baryons would be precisely by using such a two-fluid approach that also exists already in literature. Okay, finally, I want to also say something about the weak worm case. And I want to, I don't know, is Connie, is he here? Ah, here, okay. Yeah, so this is based on the review, and which I found quite interesting, because my background is not plasma physics. I'm doing fluid mechanics, cosmology, and so on. But I found very similar ideas, but in a completely different perspective. So I found it very interesting. And one way of dealing with worm features of a plasma, but also, of course, in cosmology, is by modeling the thermal distribution by a collection of cold beams. Cold beams in plasma physics, or cold streams in cosmology, same thing. Yeah? And one idea is essentially like depicted in this graph here. So then it's called a multi-beam multi-array, basically. And very similar techniques have been also done in cosmology. Not very active, I have to admit, because there were some problems in these early works. But I think this paper, they also do quite some simulations on this already. The first one, not so much, but the next one already. So I find this very interesting because in principle, the idea is to model like the weak warm features that we see in cosmology, especially with massive neutrinos. They're not really warm in the plasma sense, but they're actually fairly cold, but not completely cold. So they are sufficiently, the presence is sufficient to be worried about it. So, and one way to deal with that would be with such a multi-beam approach, for example. Okay, so I conclude now. And so I try to give you like an overview, at least from kind of my perspective, where we stand in cosmology, from the understanding of what you can do with Vlassov-Poisson systems. And yeah, lots of other problems, of course, one that are related to it that I didn't even touch today. So if you have any other generic questions, I will try my best to answer it if I can. But in any case, there are lots of methods that are developing the last few years. I mean, so what I want to just tell you that what we're doing is not just like an exercise for mathematics. So it's actually things that we can exploit directly. And one thing is essentially, again, related to simulations. No matter if you do like a n-body simulation, particle and cell simulation, or something a bit more advanced, like a hydro simulation, you need to provide very accurate initial conditions. So this is one thing, for example, a very straightforward application that we already exploited the last few years. And there are lots of things that are also now in action in cosmology between hybrid approaches, between theoretical modeling and simulations. Hybrid approaches, because sometimes a theory can predict you very quickly like the right answer or a very good qualitative answer, whereas the simulation is very costly, especially if you need to run not just one simulation, but you need to basically run thousands of simulations because you need to track the whole phase space or the parameter space. Yeah, I mean, you have like lots of free parameters, and in simulation you need to specify all the parameters. This is very costly in simulations because you can do it only for like a couple of parameters at once. Yeah. And so there's like a lot of things happening there as well with hybrid approaches. Very active, interesting area, I find. And of course, we are still very far off from understanding theoretically what's happening actually in a halo. I mean, it's just very honest. I think we have fairly good confidence that the simulations are in the right direction, but yeah, there's still a lot of things one has to check and also see if this all things are calculated in an efficient way. So this is a very important thing because we have so many unknowns. We basically want to constrain all these free parameters, how much dark matter we have, how much dark energy, and so on. So we want to know a lot of details, and we need to do this in an efficient way. Otherwise, it's a time waste. Yeah. And there are lots of future directions that one I think should do. One idea, of course, is also now with the present meeting to see if there are some approaches that are somehow touching like topics in cosmology and in plasma physics or fluid mechanics. So I think this is very interesting because my own experience is that even in cosmology, it's nowadays it's very difficult to keep track of all the literature. And if you now try to do the same thing through all the disciplines of physics, it's completely lost, of course. Yeah. And I think very important are these meetings where one is where one is trying to explain things in a simple way so that it can be transferred, if possible, the knowledge. I think this is very crucial. And for that, I also thank the organizers again of this meeting. Yeah. And yeah, hope to have some interesting discussions in the next few days. Yeah. Thank you.
Right, we've had a lot of questions, but we may have more.
In classical plasma physics, the phase considered as an n-body system.
Yep.
And the Vlassov-Poisson description is an
Yep.
approximation of the two dynamics. So in some sense, solid solving this equation by Lagrangian approach in some way going backward toward the cruise, except that the field is called Rampf.
Yeah.
So I would like to know as to dark matter, is it possible to consider it as a set of particles or
Sure.
really?
Sure, yeah, but the problem is the following. I mean, I completely agree with what you said. Yeah? Regardless if you think that the true nature of your system is particles or not, we of course can deal with particles too. Yeah. So depending also a bit on the what exactly is dark matter. So that there are lots of candidates. I didn't mention actually one of the most extreme candidates would be primordial black holes. They can be very heavy. Yeah. They can be like on the range of solar masses, yeah, or even more in principle, but it's a bit disputed. It's a bit unclear if this is really like a candidate. But in principle, if the mass of the dark matter particle would be huge, then it would be meaningful physically to actually take care of particle properties. But since we are usually interested in cosmology on ultra large scales, so even if a dark matter particle is a solar mass heavy, or even like tens or hundreds of solar masses, we are still very far off from the regime where we have to take care of particle features, because they're essentially integrated out in our description. It's because we have applied a limit by taking like a limit between the interested scales that you want to resolve and the possible scales that could appear essentially because of particle properties. They can be much more crucial in plasma physics. I don't doubt that, but in cosmology, it is less of a problem, at least if the mass is really like in the expected range.
In your introduction, you mentioned the passage from the Einstein-Boltzmann to Vlassov-Poisson, and
yeah,
if this passage done with the theory that there are particles, or is it done in another way?
So I didn't really understand the whole question. You talk about the transition between Einstein-Boltzmann and Vlassov-Poisson.
Yeah, yes.
Yeah.
In your introduction, you
Yeah.
said that at some stage when there's fused Einstein-Boltzmann,
Yeah.
and then when the system cools down,
Yes.
it's possible to use Vlassov-Poisson. But in the Einstein-Boltzmann view, is the system made up of particles?
In principle, also on a phase-space level. So everything what you see in the literature to early universe physics, like decoupling physics, these pictures from Planck, the theoretical understanding is based on the continuum approach. Yeah. So I'm not aware of like an early universe particle approach really. Yeah. But what I'm aware is, of course, people taking like worm features seriously. They check that very in detail. A couple of papers. This is more like what many people try to investigate. Sure, yeah. And in principle, I know at least from a few papers but I'm not sure if they're really helpful for your concern. But there are also ways to deal with discrete particles in general relativity. Coupled to Boltzmann, I'm not sure if that exists, but with general relativity, in principle, I know a few approaches that can deal with these kind of discrete particles, which, I mean, naively speaking, might be a challenge, because if you have a discrete particle that has essentially no extent, you essentially have a strong jump in the curvature. That can have problems, of course, yeah. Yeah. But yeah, such things exist, yeah. But not with Boltzmann. Yeah.
Right, let's have a different question. DM.
You showed those very nice solutions, theoretical solutions and computational just after shelf crossing. Have you how effective would it be to just before shelf crossing switch back to your Einstein-Boltzmann, where you probably would not have singularity or less severe singularity cross the shelf crossing part, and then go back to your Vlassov-Poisson?
You want to see like a figure like this?
No, I'm asking in order to avoid the singularity which comes with the Vlassov-Poisson.
Yeah.
Just before sharp crossing, if
Yes.
you were to go back to Einstein-Boltzmann, you probably should not have that singularity, right?
No, I don't think this is what we expect. I mean, honestly, this is a very important question. Doing these kind of investigations on the level of GR is, I think, in principle, one should do it. Yeah? And I've also worked on related problems in GR, but not on this in particular, because even the Newtonian setup is quite a challenge, I would say. So this would be now dealing with I mean, if you think about this description from the theory point of view, this would be a next level one should definitely investigate. But what you expect is that as long as the curvature remains finite, there should be no problem on the GR side. But I don't expect that things are getting less problematic. My experience is I worked a lot in the intersection between Newtonian physics and general relativity. Whenever I do things in Newtonian gravity, things were a bit easier than in general relativity, but things that, they don't get cured in general relativity. Yeah. There are more problems, unfortunately.
Yeah. You mentioned it a little bit, but it doesn't seem that general relativity is very much involved in this story.
Yes.
There is a defined baskets somewhere, so I was surprised that it's not the case. Is it because of the scale of this similarity?
So the crucial point, I did not mention this at all, but this is a completely valid question, of course, is that the curvature on the scales that we are considering, so the spatial curvature is very small. So we are in a weak field limit. So if you go, for example, down to like galactic scales, to the center of the galaxy, we of course have strong gravity regime. So, or like if you think about all these news about black holes spiraling, this is like strong gravity regime. This is not what we can do here with these techniques. Of course not. Yeah. For this, you need like really full-fledged numerical calculations in full GR. And I mean, I know a little bit about this, but I'm not working on it really. So yeah. But luckily, on the scales that we are interested in, we are really far off from any strong gravity regime. And that gives also the hope that despite of having these kind of extreme events with extreme densities, we are still seemingly in a weak field limit. And this is also why we know actually quite well that how we can translate things as well, yeah, between Newtonian physics and weak field gravity, yeah, because the strong gravity regime is completely different problem. Yeah.
Do you know the nature of this singularity? I know you had the plot, you had that the reference to Don Sykes. You know what the nature of this singularity is?
Yeah, we know. Yeah. So I'm not sure which one you're referring to. I mean, there's so the singularities of the shell crossing is exactly these ones here.
Yes.
These so far we have not used Don Sykes. We used asymptotic methods basically to calculate the leading order asymptotics, but we know that. So we know, for example, that I don't know which one. There are two different types. This type and this time here. And then there was another one because of the asymmetry. Let's forget about that for a moment. But one of them behaves like t minus t star to the power of 5 half. So if you take 3 derivatives in time, then it turns into a square root t minus t star, and that blows in your 1 over square root of t minus t star, and that blows up. So we know the asymptotic behavior.
Well, I think there are a couple of more questions, but I have nearly 11 and we need some coffee. So I propose that people chat with him during coffee.
Yes, yeah.
And let's thank Cornelius again.
Let's reconvene at 10 past 11. So we have time for